Every second of every day, billions of electric motors quietly power our world. They spin the fans that cool our homes, pump water through our cities, drive factory robots, move elevators, propel electric vehicles, and operate countless machines that modern life depends on. Yet, despite using them every day, very few people have ever seen what happens inside one. How can invisible electricity create powerful motion? How does a machine made from steel, copper, and magnets begin spinning the instant electricity is applied? Today, we'll journey inside an electric motor and discover, step by step, how each component works together to transform electrical energy into mechanical motion. Before understanding how an electric motor works, we first need to understand its major components. Although motors come in many shapes and sizes, most share the same basic structure. We'll explore each component individually before bringing them together to see the complete working principle. First, we talk about the stator. The stator is the stationary outer section of the motor. It never rotates. Instead, it provides the foundation for the motor's magnetic system. Its carefully designed steel core supports the copper windings and guides the magnetic field that ultimately drives the rotor. Without the stator, the motor could never generate controlled motion. Now we move on copper windings. Wrapped around the stator are hundreds of turns of insulated copper wire. Copper is used because it allows electricity to flow with very little resistance. These windings are the heart of the motor. When electrical current flows through them, they create powerful magnetic fields. Those invisible magnetic fields become the source of all motion inside the motor. Now, let's discuss the important term, magnetic field, in case of motor, which is a key factor of working. Electric current flowing through the windings immediately produces magnetic fields around each conductor. As multiple coils work together, their individual magnetic fields combine to create a much stronger magnetic field inside the stator. In many motors, this magnetic field rotates continuously. Although invisible, it is this rotating magnetic field that provides the force needed to drive the rotor. Next part is rotor. At the center of the motor is the rotor. Unlike the stator, the rotor is free to rotate. Depending on the motor design, it may contain permanent magnets, aluminum conductors, copper windings, or laminated steel. The rotor never creates motion by itself. Instead, it responds to the magnetic field generated by the stator. Now we talk about the bearings. Supporting the rotor are precision-engineered bearings. Their job is simple but essential. They reduce friction, keep the rotor perfectly aligned, and allow it to spin at extremely high speeds with remarkable efficiency. The next part is the shaft. Connected directly to the rotor is the shaft. As the rotor spins, the shaft carries that rotational energy outside the motor. This is the component that ultimately drives fans, pumps, conveyor belts, robots, electric vehicles, and countless other machines. Surrounding every internal component is motor housing. It protects the motor from dust, moisture, vibration, and impact while helping remove heat generated during operation. The housing keeps every component securely aligned during years of continuous use. Now that we've explored every major component, it's time to see how they all work together. At first glance, an electric motor looks like nothing more than carefully machined metal parts assembled inside a protective housing. But the moment electricity is applied, everything changes. The journey begins when electrical current enters the motor through the power terminals. The current is then directed into the copper windings wrapped around the stator. These windings may look like ordinary coils of wire, but the instant current begins flowing through them, they create magnetic fields. This happens because every electric current naturally produces a magnetic field around the conductor carrying it. A single wire creates only a weak magnetic field. But by winding the wire into hundreds of tightly packed loops, those individual magnetic fields combine together to produce one much stronger magnetic field. Instead of energizing every winding at the same time, the motor energizes different groups of windings in a carefully controlled sequence. As one group becomes energized, another switches off while the next group turns on. This rapid switching causes the strongest magnetic field to continuously move around the inside of the stator. Rather than remaining fixed in one position, the magnetic field now rotates around the motor. This rotating magnetic field is the heart of every electric motor. At the center of this rotating field sits the rotor.
Unlike the stator, the rotor is free to rotate. Depending on the motor design, it may contain permanent magnets, conductive bars, or its own windings. No matter the design, the rotor is constantly influenced by the rotating magnetic field surrounding it. Nature always tries to align magnetic fields. As the magnetic field inside the stator moves forward, it pulls and pushes on the rotor. The rotor immediately attempts to follow it. But before it can completely catch up, the magnetic field has already moved ahead again. So the rotor continues chasing the moving magnetic field. This continuous attraction and repulsion keeps the rotor spinning without interruption. As the rotor spins, the shaft connected to its center spins at exactly the same speed. The shaft carries this rotational energy out of the motor and delivers it to the machine being powered. It may turn a fan to move air. It may drive a pump to move water. It may rotate the wheels of an electric vehicle. It may operate a factory conveyor belt. Or it may control the precise movement of an industrial robot. Meanwhile, the housing protects every internal component from dust, moisture, vibration, and mechanical damage while helping remove the heat generated during operation. In short, all of these components work together continuously. Electricity flows into the windings. The windings create magnetic fields. The magnetic fields rotate around the stator. The rotor follows that rotating field. The shaft transfers the resulting mechanical power, and the machine connected to the shaft performs useful work. This entire process happens every second the motor is running. There are no explosions, no burning fuel, no pistons moving back and forth, only the invisible interaction between electricity and magnetism transforming electrical energy into smooth, efficient mechanical motion. That simple idea is why electric motors have become one of the most efficient and important machines ever created. And although different motors use different methods to produce this rotating magnetic field, they all rely on the same fundamental principle. Electricity creates magnetism, magnetism creates motion, and motion powers the modern world.